Hi folks, so today's topic is trinomials with common factors, and we're going to be actually factoring those trinomials, and then we're also going to talk briefly about subscripted variables, which is really another way of kind of thinking about how to differentiate different kinds of unknowns or variables. So let's take a look at this first example. Here we have x cubed plus 6x squared plus 5x. Now our job is to factor that trinomial. Now, one of the things that I notice right off the bat is that it looks like of these three terms within this trinomial, they have an x in common. So what I'm going to do right off the bat is factor that out. So I'm going to take that x and I'm going to factor it out, leaving whatever's left over when I remove an x. So in the case of x cubed, that becomes an x squared because x times x squared gets you x cubed, plus 6x plus 5. And again, after kind of looking at this, you can say, oh yeah, x times x squared would get me x cubed, x times 6x would get me the 6x squared, and x times 5 would get me 5x. Next, I'm going to look at this and say, okay, well, what other things can I do? Well, if I look at this trinomial that's inside my parentheses here, I can think about how I could factor that, kind of like what we were doing a couple lessons ago. And if it's helpful, what you can do is you can use one of these box diagrams here and see if you can factor this. So what we do know is that the first term is going to multiply to x squared, and we know that the last term is going to multiply to be 5, and our two middle terms are going to add together to be 6x. So what can I figure out? Well, I know that x times x is going to get me my x squared, and now I've got to think to myself, okay, what two values are going to multiply to be 5 and add to be 6x? And I think I've got it here, 5 and 1, and so that would make 5 times x 5x, and 1 times x 1x, or just x. And this is exactly what I want, so now I'm just going to rewrite those. Again, not forgetting my x that's on the outside. But I've got x plus 5 times x plus 1. And so this is it. It's the fully factored version of that original trinomial. Again, seeing if I can factor out a monomial, which is the x, and then continuing to factor that remaining trinomial into two binomials. So now let's try again with this one down here. So this time, when we look at the 4bx cubed plus 4bx squared minus 80bx, again, I'm going to start with a monomial and see what I can factor out of this. I notice that 4 seems to be the greatest common factor of 4, 4, and negative 80. I also recognize that there's a b in each of these terms, and there is one x in each of these terms. So what that means then is that the GCF would be 4bx. And when I factor that out, now I got to figure out what would be remaining inside. So for that first term, I'd have to multiply times an x squared. For the second term, looks like I'd just be adding an x. And for the last term, looks like it would be a negative 20. Negative 20 like that. Okay, and again, you can always kind of go back to this and say, okay, if I distributed that 4bx to each of these terms, would I be right back where I started? And that's kind of a good way to check yourself as you go along. Now I'm going to see if I can factor this trinomial, the x squared plus x minus 20. I'll go ahead and use that box method again. And so I know again that my first term is going to be an x squared. I know that when I multiply them together, the last terms I'm going to get negative 20. I can kind of piece together that x times x is going to get me my x squared, so I know the first term. And now I got to figure out the last term. So I need two things that are going to multiply to be negative 20 and add to be positive 1. So two things that are, let's see, looks like we'd be talking about probably a 5, positive 5, and a negative 4, like so. So that would be 5x and negative 4x, and when I add 5x and negative 4x. That gets me the 1x that I want. And 5 times negative 4 is negative 20. So that means that I can break this apart into two binomials. And that looks like this. And here's my final answer for that, fully factored. All right. Now down here, kind of an interesting situation with this example. The next example, because we have a negative x squared plus x plus 20. And one of the things that I could do here is I could factor out a negative 1, because just as a formality, we typically want to have that x squared be positive. So if I did that, then that would essentially change the sign of these terms, right? And now I can think, okay, what else can I factor out of this? So again, I'll go to my little box here, and I know that when I multiply the first terms together, I'm going to get an x squared. I know when I multiply my last terms, I'm going to get a negative 20. So I got an x and an x. Okay, so this looks kind of familiar, except now when we add them together, we need a negative 1 instead of a positive 1. So that means, looks like negative 5 and 4 are going to be it, right? Negative 5 times 4 is negative 20. And 4x plus negative 5x actually gets me negative 1x, which is what I want. So in the end, we end up with x plus 4, x minus 5, like so. Okay, so that's some factoring. Again, kind of trying to think about that monomial first, and then factoring the trinomials into two binomials. That's kind of the skill we're looking at. So let's look at this next example. So we have a system down here, and it looks kind of familiar. In some of our old systems, we're using x and y for variables. This time, we're actually using two different subscripts. And so if you look at the two subscripted variables we have an n sub n, and we have an n sub d. And these, yes, they have n's, but because their subscripts are different, we're actually going to treat these as two different variables, which means that when we solve this thing, we've got to solve for n sub n, and we have to solve for n sub d. They're two different variables. They're just subscripted n's. And so, just like we were using, it says we need to use elimination. Now, just like we were talking about before, in order to use elimination, we need to have opposite coefficients. And so right now, I look down here and I say, okay, well, I could eliminate the n sub n's, or I could eliminate the n sub d's. I'm going to choose to eliminate the n sub n. So right now, on top, we have a coefficient of 5, which means we need to have a coefficient of negative 5 on this bottom equation here, so that when we go to add them, we'll eliminate the n sub n's. So what I'm going to do is I'm going to just multiply each side by negative 5 of that second equation in the system. If I do it to one side, got to do it to the other, right? And so we end up with negative 5 n sub n plus negative 5, or maybe I should just do minus 5 n sub d equals negative 80. And so now I have the opposite of 5 n sub n, just like I wanted. So what I'm going to do now is I'm going to just rewrite both of those equations from my system. So the first one we didn't change, so that's there. The second one we did. Remember, we switched this to its equivalent equation down here. So we've got negative 5 n sub n minus 5 n sub d equals negative 80. And now I'm going to add these up. And just like I wanted, my n sub n's become 0, which means that they're no longer there. 10n plus negative 5, 10n sub d plus negative 5n sub d is 5n sub d, and 125 plus 180 gets me 45. And now I have something that I can solve. 5n sub d equals 45. I can divide each side by 5 to solve for n sub d, and that would make n sub d equal to 9. And now, all I have to do is plug 9 in for n sub d into one of my equations from the system, and I will have solved that system. And so I'm going to just pick the one that I circled up here, because that seems like the most straightforward, and just substituting in 9 for n sub d, like so. Put a line here just to make sure that we can see the difference. And pretty simple, I can just subtract 9 from each side, so I get n sub n is equal to 7. So in the end, my final answer here is n sub d equals 9, m sub n equals 7, and I have solved this system.